Okay, in this video, I'm going to give you an introduction to quicksort. So once again, the problem is given an array, we want to sort it in ascending order. Okay, so given an array, we want to sort it in ascending order. So one example is if I have the array 3, -2, -1, 0, 2, 4, and then 1. After I sort it, I should be given an array of -2, -1, 0, 1, 2, 3, and then 4. And one way we can do this is by using something called quicksort. And quicksort is pretty similar to merge sort in the sense that it is a recursive sorting algorithm. And also similar to merge sort, we pretty much want to specify a range in which we want to sort. So remember how in merge sort we're going to cut it in half every time, and then we're going to specify which half we're going to be sorting. And so let's look at an example. So let's say we wanted to sort between the indices of 4 and 6 in this array. So my L, my left pointer, is going to be at the index of 4, and my right pointer is going to be at the index of 6. And once I use the quicksort algorithm, I should be given something like this, where between the range of L and R, the subarray is sorted. And so if we wanted to sort the entire array, you can see that all we have to do is set L to be 0 and R to be n-1, where n is the size of the array. And once we perform quicksort on it, the entire array should be sorted. Okay, so let's look at some pseudo implementation on how we might do this. Okay, so the first thing that we're going to do is it's going to be a recursive method. So the first thing that we should have is our method header. And so it's going to be void because it's going to sort my array for me. So we're going to pass in the array that we want to sort, the left boundary, and the right boundary. So these are the pointers pointing to the specific subarray that I want it to be sorted. Okay, and since it's recursive, let's handle the base case. So the base case is going to be if L is greater than or equal to R. That just means that our subarray only contains one element or no elements, right? And if L is equal to R, that means it's pointing to the same element. So one element or no elements. Then all we have to do is return. Okay, and for the transitions or the recursive calls, let's look at an example where L is equal to 0 and R is equal to 6. In this case, what we're going to do is we're going to partition the array. And so you might be asking, what exactly is partitioning? Well, let's look at that in a little bit. But so what we have so far is our method header, we have our base case, and then all we have to do is partition our array. And what that's going to do is it's going to return an index that we'll look at later. So we're going to look at what this does in a little bit. Okay. And so there you go. So the question is, what exactly is partitioning? Okay. And the first step, and what I'm going to do actually, is I'm going to have an array already set up for you guys. So this is my array that I want to sort, where L is going to be pointing to the first element, and R is going to be pointing to the last element. So the first step for partitioning is to pick something called a pivot. And in this case, we might pick the last element, and that's exactly what we're going to do. So let's pick the last element. Okay. And the goal of the partition function is to divide this array into two groups. The first group is basically going to be all elements less than the pivot, and these are going to come to the left. And the second group that we want are all elements greater than or equal to the pivot. And these are going to come on the right. So as you can see here, I have all the elements selected that are less than the pivot. And what we want to do is create another group that's going to be greater than or equal to the pivot. So those are these elements here. Okay. And then after the pivot function is run, the array should look something like this, right? So that's essentially, here you're going to see that all the elements are on the left of the pivot. So once again, we selected one or the last element as our pivot at the very end over there. And we took all the elements that are less than the pivot, so -2, -1, 0. And we're going to put that on the left of the pivot. And then we're going to take all the elements that are greater than the pivot, so 2, 4, and 3. And what we're going to do is we're just going to put that on the right side of the pivot. And as you can see, it's fully complete where 1 is in the middle, right? It's squeezed between the two groups. And one thing that you might notice is that we don't really care about the ordering of each group. As you can see on the left side, they happen to be sorted, right? Where it's -2, -1, then 0. But you should notice that on the right side, that they aren't sorted. So it goes 2, 4, and then 3. All we care about is that the elements on the left of this pivot are less than the pivot itself. And then all the elements on the right are greater than or equal to the pivot itself. And so once we're done with partitioning, we're going to return. So we want to return. So it's going to return an integer value, which is going to return the new index of the pivot. So in this case, as you can see, where that was the same array that I had earlier, L is 0, R is 6, we should notice that it's going to return 3. And I'll show you the partition function in a little second, how we implement it, but let's assume that we already have it. And so once again, you should notice that the position of the pivot is correct in the final array, because all elements on the left of it are less than that pivot value, so it's less than 1. And all the values, so as you can see on the left, they're all less than 1. And then all the values on the right are greater than 1. So that means 1 is in the correct position after this pivot function has been called. And what we're going to do is return that index. Okay. So after that, now all we need to do is take care of the left and right sections. So similar to this right here, we need to take care of the elements that are smaller than the pivot and all the elements that are greater than or equal to the pivot. So we can simply do that by calling the quicksort function on the left side from L to index -1. So once again, index is going to be the index of the new index of the pivot. So all we have to do is call quicksort from the left side to the index -1, and then call quicksort on the right side, which is index +1, all the way to the end of the right boundary. And so you can kind of think about this. This is pretty similar to merge sort. And by calling this recursively, we'll be able to sort the entire array. Okay, so let's look at how partitioning works exactly. And I'll use an array of 11 elements in this case. And let's say in this partition right here, the pivot was 10, right? Because I usually like to pick the last element as my pivot. And so in this example with the I and j pointers, you can see they're already pointing to some values. We're basically going to say that we're in the middle of running our partitioning function. And the reason I wanted to start in the middle of my partitioning function is because I think it's a little easier to see how this works. So right now we're in the middle of our partitioning, And this j pointer right here in the red is actually pointing to the current element that we're examining. And this can be simply done through a for loop, for example, right? From 0 to the index of the pivot minus 1. Or in this case, if you're doing subroutines, right? If you're doing the smaller calls, then it would be from the index of L to the index of your pivot minus 1. And once again, that would just be L to R minus 1, because the pivot is going to be R. And what we're going to say is we want to go up to all values from 0, or from the left boundary to the value right before the pivot. Okay. And this j pointer can, simply be done using a for loop. Okay. And for each iteration of the for loop, right, we want to make sure that all elements we've seen so far are separated into two groups. So, but before that, once again, the j pointer just traverses from the left boundary to the index minus 1. Okay. So what we're going to do is we're going to examine how this works. So we always want to separate the elements into two groups, or all the elements that we've seen so far into two groups. So all the elements we've seen so far can be tracked using this j pointer right here. And the first group, once again, is all the elements that are less than the pivot. And the second element are all the elements that are greater than or equal to the pivot. And we always want this index I right here. And you might be wondering, oh, why do we have this index I here? And essentially what it is this index I is going to point to the rightmost element that is less than our pivot. That's the last index of our first group. So you can see that so far we've already seen all these values. In this case, I accidentally shifted j over by 1, but we'll see exactly why we did that. So we always have two conditions that we want satisfied. The first is that all the elements up to and including I are less than the pivot. So 2, 1, and 4 are all less than my pivot, which is 10. And the second condition that I always want satisfied is that all elements between I and j are greater than or equal to the pivot. So that doesn't include I, but that does include j. So as you can see, before when I was running this partition function, the index of j was at the 12, but I moved it over by 1 because it would, for example, we would have done j++. And so once j has incremented to the 3, previously it was the 12, right? The two conditions are not satisfied anymore. And we can simply fix that by incrementing I by 1. So we'll increment I by 1, like so. And then what we're going to do is we're just going to swap the values. So we're just going to swap the values at index I and index j, like that. So now you can see that the 3 is at the I and the 13 is at the j. So now all the conditions are satisfied again. All the numbers up to I are less than the pivot, and all the numbers between I and j are greater than or equal to the pivot. So let's continue on. So j is going to increment by 1, right? And since 16 is greater than or equal to the pivot, all conditions are satisfied. And once again, let's increment j one more time. Okay, so now as you can see, 5 is less than our pivot. So what we're going to do is increment I by 1, right? And then what we're going to do is swap the values at I and j. Okay, so once we've swapped them, you can see that the conditions are satisfied. All values up to I are less than the pivot, and all values between I and j are greater than or equal to the pivot. So all conditions are satisfied. Let's increment j over by 1. So once more, the conditions are not satisfied, increment I by 1, right? And then swap the values at I and j. And so now, as you can see, we have two groups. We have the first group, which is all the numbers that are less than the pivot, which is 10. And then we have the second group, which are all numbers greater than our pivot. And now all we have to do is make sure that the pivot is between the two groups. And what we can do to simply do that is look at I plus 1, right? And then what we do is just swap the last value and this index of I plus 1. So we take the 13 and we take the 10 and then swap them. And then, like I said earlier, we need to return the index of the pivot. In this case, it would just be I plus 1. Okay, so now that we know how pivoting works, or partitioning works, sorry, let's just look at some pseudocode. So once again, we're going to have an integer function. It's going to return some integer. And we're going to have the array that's passed in, and then the left and right boundaries. What we're going to first do is we're going to pick our pivot, which is just going to be the last element of that array. And L and R are 0 indexed, so that's why we can call array R. Then what we're going to do is we're going to pick our I. So I is going to point to the last index of the first group that we've seen so far. So in this case, it's just going to be L minus 1. The reason we're going to make it L minus 1 and not L is because we actually haven't seen any elements yet. Because the J, that J pointer, is pointing to all the elements or to the last element we've seen so far. And J hasn't even started yet. So we're going to set I to L minus 1. Then what we're going to do is we're going to create a for loop that starts from L to R minus 1. So R is going to be our pivot. We don't want to check our pivot, so we're going to go to R minus 1. So we're going to start from the left boundary all the way to R minus 1. And this pointer, if any point along the way, we notice that that value is less than our pivot, what we're going to do is increment I by 1, right? Look at the first element that is greater than or equal to our pivot, and then just swap those values. So swap array I and swap array j. From there, we're going to finish the entire iteration of L to R minus 1. And then we just want to squeeze our pivot between the two groups. So what we're going to do is we're just going to swap the values at I plus 1. And remember, I is still pointing to the last element of our first group, which is all elements less than the pivot. So we're just going to swap the value at I plus 1 and the value at our pivot already. Then once again, we want to return the index of the new pivot, of the new index of the pivot, which is just going to be I plus 1. So this is the pseudocode for our partition function. Okay, now let's look at some time complexity. So to analyze some time complexity, what we need to do is look at the worst case and sometimes the best case. So what is the worst case? Well, the worst case in this case is going to be O of n squared. And why exactly is it O of n squared? Well, let's think about this. So if we're picking the last element as our partition, right? Or sorry, as our pivot, then what's going to happen is we're going to partition the rest of this array, right? From 1 to 6. And remember, the worst case is that it's already sorted, so we're not modifying anything. So what it's going to notice is that 7 is our pivot, and we're just going to have to scan through from 1 to 6. So once that's done, we're going to pick 6 as our pivot, right? And then it's going to scan from 1 to 5 now. Then that's done. We're going to pick 5 as our pivot, then go from 1 to 4. Then once 4 is our pivot, we're going to scan from 1 to 3. And this will continue on and on and on. And so once again, why is this O of n squared? Well, let's think about this. If we have to do n iterations on the first run, we have to do n minus 1 iterations on the second run, then n minus 2, then n minus 3, and then all the way to 1. What we should notice is that this can be represented in a mathematical formula, which is just n times n plus 1 divided by 2. If we expand that out a little, we should notice that it's n squared plus n divided by 2. We remove some of the extra factors, and that'll just give us O of n squared. Okay. Now let's look at the best case. So the best case is going to be O of n log n. And you might be wondering, oh, why is it O of n log n? So the reason it's going to be O of n log n is whenever we choose the best pivot, or whenever we pick a pivot, it's always the best answer. And the best answer is always going to be the median of the subarray, well, or the element that's closest to the middle. And so when we swap the values, it's going to be the perfect element. So every time we pick a pivot, do the partitioning, it's always going to update our array, and it's going to bring it closer and closer to the answer. And so what you should notice is that in the first iteration, we have n iterations. Then on the second level, because that's the perfect median, right, we just need to work on the first half and then the second half. We split it down by 2. So then on the second layer, we have n divided by 2 plus n divided by 2, giving us O of n. Then on the third layer, we have n divided by 4, n divided by 4, plus n divided by 4, plus n divided by 4, giving us O of n. And then on the last layer, we have a bunch of 1s, which gives us O of n as well. Then the height of this tree, per se, is log of n. And so what we can say is that our final time complexity is O of n log n. Okay, and then finally, let's look at some implementation details. So choosing a pivot can be done in many ways. And one way we can do this is by simply randomly picking a pivot. So a lot of people do this. What you can do is just, math.random pick a pivot between the values or the ranges that you're given. And then also what you can do is another technique called median of 3. And the median of 3 essentially just picks 3 random numbers and then chooses the median out of those 3 numbers. And this will basically decrease the probability of choosing a bad pivot whenever you're choosing a pivot. So those are the 2 implementation details that you can look out for, which is basically just choosing a pivot. Okay, so let's write the full code for Quicksort now. Okay, so here I'm in my IDE, and basically what I'm going to do is I'm going to have this sample input as my test cases. So what I have here is the first line of input is just the number of elements in my array. Then the rest of the elements, or the rest of the input, is just going to be those elements. And in this case, I have the elements 1, 8, 12, 19, 3, 5, 8, 16, and then 21. And then I'm expecting to see, after using the quicksort algorithm, 1, 3, 5, 8, 8, 12, 16, 19, and then 21 as my final array. Okay, so first let's take in the input. Then what we're going to do is we're just going to create an array of size n, and we're just going to take an input for each of those values. So array I is equal to sc.nextInt. Then what I'm going to do is I'm just going to call the quicksort function without making it yet. So I'm just going to call quicksort on my array, and my starting index is 0, and my last index is n minus 1. Then after the quicksort function, I'm just going to print out my array. That can be simply done with a for each loop. Okay, so first let's start off with the quicksort function. So the quicksort function will pass in an array. it's going to have the left boundary and the right boundary. And once again, the base case for this recursive method is if L is greater than or equal to R, then just return, because there's only one element or no elements. And otherwise, we're going to call the partition function. So the partition function is going to return an index, which is the new index of the pivot, right? So we're just going to call the partition function with the array, and then the left and right boundaries. Then once again, once we've found the index of the new partition, or of the partition, because that's in the correct position now, all we have to do is call quicksort on the left side from L to index -1, and then quicksort on the right side, which is from index +1 to R. Okay, so now let's create this partition function. So this partition function is going to return an integer. It's going to pass in an array, the left boundary, and the right boundary. And once again, what we're going to do is we're going to pick our pivot, and I'll just say it's the last element, like this. And what we're going to do is we're going to set our I to L-1, because we haven't seen any elements yet, right? And if our first element happens to be less than our pivot, then we want to increment I by 1 and then just swap those values. So we're going to start our j at L and work our way to R-1. And if along that way we see that the value at that j index is less than our pivot, we're going to increment I by 1, and then we're going to swap those values. So Java doesn't have a built-in swap function, so what we're going to do is we're just going to create a temporary variable that stores the element at array I. Then we're going to set array I to array j, and then we want to set array j to equal to array I, but we already lost it because we set array I to array j. But luckily, we set a temporary variable to array I already. So all we have to do is say array j is equal to temp. Okay. From there, what we're going to do is we're going to squeeze the pivot in between the two elements, or the two groups. So all we have to do is swap the element of the pivot, or at the pivot, and the ith plus 1 element. So temp is equal to array I plus 1. Array I plus 1 is equal to my pivot. So that's just going to be like this. Then we want to update the element at the pivot. So we're going to not say pivot, but now we're going to say array R is equal to temp, right? And this should be a capital R here. Okay, then from there, because we're returning the index or the new index of the pivot, just return I plus 1. Okay, so let's hope there's no errors in this, and let's run it. And as you can see, we get perfectly the correct answer. And in this case, once again, the best case is O of n log n. The worst case is O of n squared. And I haven't proven this in this video, but you can prove it. And you can prove that the average case is going to be n log n as well. So in this video, you learned about quicksort.